Welcome back to our lecture 3. In this lecture, what we are going to do is to look into the theory for the lasso. Okay, so I'm going to first define the lasso program, the lasso problem, give an overview of the lasso solution. Then we are going to go a little bit deeper into the theory. After that, we are going to look to extensions of the lasso, right? So here in these lectures, we are going to see kind of an overview of the theory. I will provide more detailed notes for anyone who may be interested in going a little bit deeper into the details of the results, okay? So the agenda is that we are going to look for the solution for the lasso, unix of the solution, and the lasso algorithm. That's what we are going to cover in this first block. We are going to have 4 blocks for lecture 3. Okay. These are the references. We have a very good exposition of this material in our books, Hasty, Tibshuran, and Friedman, and Buman van der Heer, and also a list of papers that covers the material. Okay? So let's start with our framework, the linear regression model. We have a predictive model, so we say that a variable y is linked to a vector variable x by a linear function. We have p regressors, so the dimension of the regressors is p, okay? And we have ut is the error of the model, okay? That's everything that's not observed, okay, is determined by this error term, okay? One thing that's important that I have already mentioned in the beginning of the course is that the dimension of the vector x, p, okay, grows with the sample size. So we allow the dimension of the problem to grow as the sample grows. And we do that in order to construct asymptotic methods that will be good approximations for situations we face in practice where the dimension of the regressors is larger than the sample size, okay? Another point that I want to stress that we are going to disregard the intercept. So we are going to set beta naught to 0. So we are assuming that the data have been demeaned, okay? And all the explanatory variables are also in the same scale. We probably have standardized the regressors, okay? So the question is, how should we estimate the parameters, okay? Remember that p could be much larger than t, so OLS is not feasible, okay? And we have to rely on a different estimator, right? And so how we are going to estimate the parameters beta here, okay? So it's important to develop new techniques. In the previous lecture, we studied REACH. REACH is a possibility, but REACH has some limitations. We are going to try to overcome these limitations today. Okay? And once we have statistical estimation procedure, we want to know what are the statistical properties of this estimated model, right? So just to remind you that we are going to work a lot on matrix notation. So we are going to like stack all the observations in vectors. So we stack the dependent variable, we stack the regressors, and we have kind of a short notation that's y equal x beta plus u. Okay? And what we know is that if x prime x is full column rank, that is, if the rank of x prime x equals to p, where remember p is the number of regressors that we have, okay? So if this is the case, we can estimate the model by OLS, and the solution is pretty simple. Everyone knows that beta hat, the OLS estimator is given by x prime x inverse x prime y, okay? The problem is that when p is larger than t, the rank condition, this rank condition here, is not satisfied anymore by construction, right? And then the OLS estimator is not even well defined, so we have to come up with a different solution. So what I have already told you is that the solution will rely on a sort of shrinkage, okay? It will be like penalized regression. One approach is REACH that we saw on lecture 2. Today we are going to see a second approach, that's lasso, and then we are going to extend lasso to some other approaches, some other ways of defining the penalty function. All right, so how lasso is defined, the beta lasso. So there are two ways of defining lasso, and they are totally equivalent. The first one is what we call the Lagrangian form, okay, or the penalized form. We define the lasso estimator as the argument that minimizes a function that consists of two terms. The first term here is just the sum of the squared errors, okay? And the second term is the L1 restriction. So I'm basically saying that the sum of the absolute values of the coefficient is a penalty term, and lambda is the penalty parameter, is the amount of penalty we want to introduce in the model. The interpretation for lambda is exactly the same as we did on REACH. Is how the bigger, the larger lambda is, the more penalty we are introducing, the smaller will be the coefficients, okay? One important point is that, contrary to the REACH, we are including a 1 over t here. Of course, it's all equivalent, but the way we are doing that is just to scale up lambda. In some papers, you are going to see also the author dividing not only by t but by 2 times t. This is just notation. So here I'm going to keep all over the slides 1 over t. Okay. So this form here is what we call the Lagrangian form. Okay. There's an equivalent way of defining the problem I have already mentioned. That's the constraint form. That basically says that the beta hat lasso is the solution to a least squares problem where we impose an L1 constraint on the parameters. So we say that the sum of the absolute values will be less than a constant penalty C, okay? And there is a relation to C. In fact, this C is C of lambda. It's not kind of a closed form solution that we can derive, but they are related. For all constraint problem, there will be a lambda that will solve the Lagrangian problem that will give the exact same solution. So they are totally equivalent. You can think about lambda exactly as the Lagrangian multiplier of this constraint form. Okay? So we are going to work with one form of the other to derive some results, and depending on what we want to show, but this will be totally clear over the slides. Okay, so that's the classical picture. You saw it before. That basically shows that the lasso program will deliver sparse solutions like zero estimates, and ridge on contrary will not. And what we are showing here is exactly both programs, the ridge and the lasso, in terms of their constrained version. So this is the constrained version, here the diamond or the ball, the circle. These are the constrained regions, okay? So basically here we are saying that the absolute value of beta 2 plus the absolute value of beta 1 is less than a given constant. And here we are saying that the square of beta 2 plus the square of beta 1 is less or equal to some constant, okay? And here what you're seeing, these lines here, they are the surface of the least square function. So if you have no penalty, what you're going to get is this solution here. This is the optimal LS solution whenever it's feasible, okay? But as we are introducing the constraint, the solution will be the intersection of these red curves with the blue diamond, okay? So you see here that we can, as we have kinks on this surface, we can get a solution that's exactly to zero. And this will not going to happen here with ridge, okay? So it's kind of a very neat way and very simple way to see the difference between lasso and ridge. So let's move for the solution for the lasso. We saw last week that ridge has a closed form solution. So we have an analytical form for the ridge estimator. This will not be the case for lasso, but we can learn a lot of things with the lasso estimator, and that's what I'm going to show you right now. Okay? So the first thing to notice is that the lasso problem is a convex program, because it's a quadratic program, the least squares, plus a convex constraint, okay? However, it's not strictly convex when x prime x is singular, okay? And x prime x will be singular whenever p is larger than t, or of course if you have multicollinearity, right? So therefore, in general, okay, the beta lasso, beta hat lasso, the solution to the lasso program is not unique. So we may have many parameters that solve the lasso program, okay? On the other hand, the predictions are unique. So x beta hat is unique, which is good news, because if you are just interested in producing predictions, okay, you don't have to bother about the fact of the estimator not being unique. Okay? Nevertheless, we have good news for you, because there is this paper by Ryan Tibshirani, which was published in 2013 in the Electronic Journal of Statistics. This paper is on our Google folder, so if you want, if you are curious, you can take a look on it. But the overall message is that if the entries of x are drawn from a continuous probability distribution, okay, then the lasso solution is unique with probability 1. So if we introduce some restrictions on x, then we can guarantee that the lasso solution is unique. So and these restrictions are pretty mild. In the paper, in fact, the restrictions are a little bit more technical, okay? and more general than what I'm stating here. But I think for the sake of our comprehension, saying that if the entries of X draw from a continuous probability distribution, we cover most of the cases of interest, right? And another important point here, and we are going to discuss more this issue later, is how many non-zero coefficients the lasso solution can give us. And the answer is that the lasso can give only the minimum between t and p. So if p is larger than t, so if we are in high dimensions, the number of non-zero coefficients of selected variables, okay, will be restricted to t. So it will to be restricted to the minimum value between t and p. Okay? In some situations, this may sound a little bit too restrictive, okay? And we are going to see methods that may overcome this limitation. We are going to see a specific one solution to this on our block 3. Okay? Right, so any lasso solution, beta lasso lambda, okay, must satisfy this condition. So 1 over t x prime times the error of the lasso estimator. So this thing here is u hat, right? Is the estimated error. Okay? So 1 over t x prime u hat should be equal to lambda, and this SG term, SG is a shorthand for a subgradient, and I'm going to give you more details about that in a second. So SG is a vector with p entries, okay, and each element of SG will be either one of the three, will belong to one of the three sets. It will be equal to 1 whenever the lasso estimator is strictly positive. It will be equal to -1 whenever the lasso estimator is strictly negative, and it will belongs to the interval, the closed set, -1, 1, whenever beta hat lasso equals to 0. Okay? Where are these quantities coming from? So basically, how we find a solution to an optimization problem, a convex problem. We derive the cost function, we equate the derivative to 0, and we solve for the parameters, right? That's the way we proceed to find the OLS estimator. This is the way we proceed to find the reach estimator. Okay? In these two cases, okay, the cost function is differentiable. Okay? With the lasso, things turn out to be a little bit more complicated because of the penalty term. The penalty term is an absolute value. Okay? And how we will take the derivatives of an absolute value function. And the answer to that is based on something called sub-differential calculus, okay? That I'm going to give you just kind of a glimpse of how these things work, okay? So basically, what you're seeing on your screen is the solution for the lasso program based on subgradient optimality. Okay? So this SG vector belongs to the derivative of the subgradient of the L1 norm. So is the derivative of the L1 norm of the coefficients evaluated at beta hat lasso. And what's the subdifferential? So we define the subdifferential that we're going to say that it's calligraphic D F evaluated at the point x naught. It will be the closed set between D minus and D plus, okay, where D minus and D plus are the one-sided limits, okay, left and right derivatives of f of x at x naught. So here is D plus, okay. So D minus is the left limit, okay. So here we are looking at D minus, is the left limit of f of x minus fx naught divided by x minus x naught, where D plus is the right limit of the same function. So we are looking to limit coming from both sides, okay? And the subdifferential at the point where the derivative, the usual derivative, is not defined will be a set that will be defined by this limits D minus and D plus. Okay? So the subdifferential is a set valued function. Okay, it consists of a single value, of course, if f is differentiable, or it will be an interval of values, or even it will be empty if we have D minus larger than D plus, okay, or vice versa. All right, so basically the essential results of optimization can be extended to these semi-differentiable functions, okay. So if f is a semi-differential function and x naught is a local minimum of f, then 0 belongs to the subgradient, to the interval defined by D minus and D plus, okay, that we saw on the previous slide. Okay, as with regular calculus, the converse is not true in general. Okay, so here we can see a picture. Okay, you have points where you have the function is differentiable. So what's the derivative is the tangent line touching this specific point. But you can see here, this point here is a kink. So the usual derivative is not defined, so we can have many tangents. But they're kind of limited by the tangent, this tangent here, and this other there. So it'll be something, if you rotate these things in this direction, okay, the subgradient at this point here will be any of these tangent limited by these the two limits, right? So for the absolute value function, okay, what we have, so if we draw here the absolute value function, okay, for all points but the origin here, okay, we have the derivative well defined. Okay, so if x is negative, so we are in this region here, the subgradient will be -1. If x is strictly positive, we are in this region here, the subgradient will be equal to 1. The problem is this point here. It could be anything between +1 and -1, because this is the tangent to the point, This is also tangent to the same point. So any tangent between these two limit tangents would be a viable tangent, okay? So for the case of x equals to 0, we have the subgradient being this set value function between -1 and +1, okay? This looks like a complicated thing, but will allow us to derive many properties of the lasso program, okay? So this is a very important slide here now. Okay? So the beta hat lasso minimize the lasso function if and only if it satisfies the Karushkin-Tucker conditions, the first order conditions, as in the usual optimization problem where you have differentiability all over the parameter space. But here, instead of just taking simple derivatives, we are going to compute the subgradient, okay? So what are the first order conditions? Okay. We're going to take the derivatives of the cost function. So there is one component is the derivative of the sum of the squared errors, and another component will be the subgradient of the absolute value function. And when we should take the derivatives of these cost functions and make it equal to 0. So basically we are going to say that the derivative of the sum of squared errors should be equal to minus the subgradient of the absolute function. So that's what you're looking at on your screen. On the left hand side we have the derivative of the sum of the squared errors, so the derivative of the L2 norm squared of y minus x beta. So the derivative with respect to beta j, one specific coefficient, evaluated at the lasso estimate for this specific coefficient. Okay? And on the right hand side you have the subgradient of the absolute value function. But we have two cases. The first case is whenever the estimated coefficient, the point estimate, is different from 0. So we are in the regions where we can take the derivative of the absolute value function with no problem. So in this case, the subgradient will be either 1 or -1 depending on the sign of the estimated coefficient. So this will be equal to lambda, and the sign function of beta hat j. If it beta hat's positive, this will be equal to, this sign function will be +1. If beta hat is negative, this will be -1. And this is for the case, as I have already mentioned, that beta hat j, this specific coefficient, is different from 0. On the other hand, if beta hat equals to 0, what we're going to have is an inequality, because we can have here anything between -1 and 1, so the derivative of the squared loss will be less or equal than lambda. So these are the first order conditions. So we can compute here the left hand side of these two equations, and what we have by the end of the day, okay, is that the first order conditions will imply two conditions. Okay? Let's start with the second one here. What this condition is saying? Remember what we have here. This is exactly the estimated residuals. Okay? This is once you have a beta hat, this is an estimator of the error term in our linear regression model, right? And so we are saying that whenever the absolute value of xj prime u hat, okay, divided by t is less or equal lambda divided by 2. This 2 we can remove it from here. We can put it here. Okay. Whenever this happens, it's because the coefficient related to this j variable here. Okay. So this is the column of the matrix X related to the jth variable. Okay. So whenever this happens, it's because the associated coefficient is 0. So what this quantity means, this is kind of a sample estimator of the covariance between one of the covariates and the residual term. So whenever this covariance is below a certain threshold that is determined by lambda, the coefficient will be equal to 0. Okay? If this covariance is larger than this threshold, then we are going to have non-zero coefficients. So this is really, really important because people tend to believe that the zero coefficients are directly related to lambda. And I see several papers saying that, the coefficient of one specific variable is 0, is estimated as 0, because of the true coefficient is less than lambda. Okay? This is not true. There's nothing on that slide that supports this claim. Okay? It's not a relation that involves just the coefficient. One, it relates the covariance between regressors and the residual term. So that's the first thing. Of course, there could be special situations where this will translate to a condition on beta hat. Okay? But even more important than that, these conditions here are all on beta hat. They are not on beta naught. So we are making no claims here about the true coefficient. Okay? So there's nothing related to the true coefficient beta naught on this slide. So this is really important. Okay? So as I mentioned, there's it's a covariance, but we can state the result in terms of correlation. The correlation between a predictor and the residuals must have certain minimum threshold that's related to lambda before it's included in the model. That's basically what we are saying here. Okay, if this correlation is below a certain function of lambda, then beta hat lasso will be equal to 0. Okay. Of course, in very specific cases, we can make this a little bit simpler. Okay. So if P is less or equal than T, okay, and 1 over T x prime x equals to the identity, okay, we can write down a solution for the lasso problem in terms of the soft threshold estimator. Okay? So basically, the beta hat lasso will be the sine function of this variable zj here, where zj is defined here. Okay? times, okay, look at this notation here, we have a plus sign here, that will be the maximum between the discrepancy between the absolute value of j and minus lambda over 2 and 0, and this is what we call the soft threshold estimator. Okay, so whenever the absolute value of zj is less than lambda over 2, okay, then this will be 0 and beta loss will be 0. Okay? And now we're going to show why the confusion arrives, because what is exactly x prime y over t is exactly the OLS estimator whenever this is true. Remember that we are looking at p less than t, so recall what's the OLS estimator. X prime x minus 1 x prime y, right? Divide the inside of the inverse by t, so this is equivalent of dividing here by t. So this is innocuous because we are dividing the inverse by t, so this t goes outside the parentheses here and will cancel with this t here. Okay? But what the assumption we make is this whole thing here is identity. So the inverse of the identity is identity, so we have the OLS estimator is 1 over t x prime y. So basically what this result is saying that whenever the OLS estimator of a coefficient is less than lambda over 2, okay, then the estimator of the lasso will be 0. Whenever the OLS estimator is larger than 2, then the beta lasso, larger than lambda over 2, then beta hat lasso will be different from 0. But this only happens because we are dealing with p less or equal than t, so beta OLS is well defined, and because we are working with very specific set of variables. We're basically saying that these variables are uncorrelated and have a bound variance. It's a very specific variance here, unit variance. Okay, so this is not true in general. In general, the result is this one here. Okay, so it's a much general condition, and it's not related that specific with a coefficient, and it's nothing to do with OLS coefficient here, because in these situations OLS is not even defined because we have p larger than t. Okay, so keep this in mind to avoid confusion. Okay, so if you have doubts in our live session, please ask questions. Come to the office hours and try to solve any doubt you may have about this. Okay. So this is the soft threshold function. So there's a region where you're going to make the coefficients equal to 0, and other regions you are going to make it different from 0, but bear in mind that there is kind of a difference here between the 45-degree line, the black line here, and the dashed blue line there. Okay. So again, for this orthonormal case, we can write the beta hat Lasso solution as here, and here's a plot for different values of lambda. Okay, and you see how the restriction is kicking in. So the usual solution for this problem, the true value of the coefficients is 0.5. Okay, so if you have a very mild penalty like lambda equals to 0.1, the minimum here is close to 0.5. Okay, as we increase the values of lambda, you see that the minimum of the cost function is going into the direction of 0, and in the limit here where lambda equals to 1, you see that there is a clear kink here. Okay, so we can amplify this for you to see that there is a kink here. Okay, right? All right, we can also look at what we call the lasso path. I have presented a similar picture for the ridge, and now I'm presenting for the lasso. So we have a simulated data from a linear regression model with P covariates and T observations. Okay, so we have like 10 covariants and 100 observations, and this is pretty low dimension. Both X and U come jointly from a normal 0-1 distribution. And basically what I'm doing here, I'm on the X-axis, we have lambda, so increasing the value of lambda. And on the Y-axis, we have the lasso estimates. So if we have no penalty, we have here is the estimates, for instance, of this coefficient. As we increase the penalty, you see that the lasso solution is decreasing because we are increasing the amount of shrinkage, but the path is linear. It goes linearly to 0. Okay? So in fact, the lasso path is piecewise linear. This is fact 1. And fact 2, it's possible to compute a threshold where all the coefficients will be equal to 0. If we set lambda larger or equal than 1 over t, the infinite norm of x prime y, so basically we're saying the maximum covariance between regressors and observations, okay? All the lasso estimates will be equal to 0. So it's clear what it's the maximum amount of shrinkage that you want to include in the model. Okay? This is the same sort of picture, but now we have only 5 observations in our 10 coefficients, and what you see is that lasso sets a bunch of them to 0. So most of them are 0 from the beginning. So you see that you have 1, 2, 3, 4 non-zero coefficients, and it goes linearly, piecewise linear to 0. There's one curiosity here. You see that all the other coefficients are going to 0, are decreasing as we increase the amount of shrinkage. But there's one here that for some values of lambda, it increases and then it decreases again. Why this is happening? Can you think about an explanation? The reason is due to correlations among regressors, okay? And we are shrinking, right, the absolute value, the sum of the absolute values of the coefficients. So the L1 norm is being shrunk, okay? But one specific coefficient may grow, but this growth will be compensated by a decrease in another coefficient in such a way that the L1 norm is minimized. Okay? We're going to see more about that later. So how we can look into more details of the solution of the lasso program. So let's assume that first that X is such that the lasso solution is unique. Okay, let's call A the support of the solution of the lasso. Basically, that's the active set, so the number of non-zero estimated coefficients. Okay, I'm using a different notation here that I use when I define sparsity. We define sparsity in terms of S, but S is the true sparsity. It's related to the support of beta naught. And here we are talking about the lasso solution, so it's beta hat. So I prefer to use a different notation, okay, a different letter to represent this. And let's define SGA as the signs of the active non-zero coefficients, if they are positive, if they are negative. Okay, so we can write the beta hat lasso for the coefficients that are not in the active set will be 0. That's what we have here. Okay, and the solutions for the active set, okay, will be given by XA prime XA inverse. What's XA is the set of active variables, the set of variables where the estimated beta is different from 0, okay, times XA prime Y minus T lambda SGA. Where this comes from, this is just the solution of the Karush-Kuhn-Tucker conditions. This is the solution of the first order conditions. Okay? No mystery here, but just making this specific difference between what's the active set and what's the non-active set. Okay? So as I have already mentioned, beta hat AC are the coefficient estimates that do not belong to the active set. Okay? So the coefficient estimates of the active set, beta hat A, are given by the OLS coefficients minus this amount here, which is exactly the shrinkage amount. Okay? Another important point is that XA prime XA will be invertible because we are working just with the active set. Okay? So the shrinkage term does not move the OLS coefficient towards 0, but it moves the L1 norm of the coefficient towards 0. And why the first bullet here, the bullet point happens, is due to correlation among active variables. Okay? However, as I mentioned, the lasso solution will deliver strictly smaller L1 norm than the OLS estimator on the active set, because we can write down, we can show that L1 norm of beta hat A will be less than the L1 norm of XA prime XA inverse X prime A. Why? Because this here is just beta A OLS hat. And remember, although we are in a large dimension setup, when we restrict ourselves to the active variables, then OLS is feasible, right? And finally, we can, so this is a result that shows, okay, lasso is shrinking the L1 norm towards 0. So what we saw in this first block, the first thing is the interpretation of the lasso solution. This is it's very important. Keep that in mind. And the second, to show that, in fact, the lasso solution shrinks the L1 norm of the coefficients. Okay? We can write down a very simple algorithm to solve the lasso program. So basically, what you do, you pick a lambda, you start with a value for beta. Here in line 1, you saw on the screen, we are starting beta as a ridge solution. Then we are going to repeat a loop that for each coordinate, for each component of vector x, what you're going to do, you're going to basically compute the difference between your dependent variable, okay, and all the other estimated regression terms here. But bear in mind that we are not taking into account, of course, the same variable. And what's this coefficient here? Is given by the soft threshold function. Okay, so what do? You work with the soft threshold function for this specific variable. You compute the beta, you compute the residuals, okay, and you work with this loop until you stabilize your coefficients. So you are searching for the lasso solutions component-wise, okay, for each component. Okay. This is a very general algorithm. There are many other algorithms out there that much more efficient than this one, but this is kind of a very simple and neat algorithm to start with a lasso, to solve a lasso problem. Okay, so that's the end of our block 1. See you on block 2.